Continuing our plan, let's carry out step 4. Remember that our assumptions in this entire context are that A is an algebra of sets on X, and that mu is countably additive, non-negative function. Remember also that we have already proven that A mu, the collection of mu measurable sets, is an algebra of sets. So we've already proven parts 1 and 2. We're going to need that to make sure step 4 works. So we already have A mu is an algebra of sets on X. So here is what we want to prove, this implication, that if A mu is closed under countable unions of pairwise disjoint sets, then A mu is closed under countable unions of any countable family of sets. And this is a general idea that is going to work for any algebra of sets. So what we're about to do works for A mu. You will see that it works because A mu is an algebra of sets. So to prove the implication, assume this. Then we'll try to prove this. Now let Bn be a countable family of sets in A mu. And I'm not going to assume that the Bn's are pairwise disjoint. So my goal is to show that the union of the Bn's is in A mu, right? Can I view that union as a union of disjoint things? Well, here's kind of what I imagine. I've got B1, right, and then B2, B3, B4, B5, etc. Well, what I can do to view the union of all of these as a disjoint union is I could start with taking B1, and then I could take just those bits in B2 that I didn't already get in B1, right? And then I could take just those bits in B3 that I didn't already get in the union of B1 and B2, and then just the additional needed bits of B4, and then only the additional needed bits of B5, and so on. So that's the idea. So define, so we're going to make C, like C1, let's call it, just be B1, and then C2 will be B2, but delete what we already got from B1, and then C3 will be B3, but then delete what we already got from the union of B1 and B2, and so on. So in other words, define Cn to be Bn, and then delete the union up from B1 up to Bn minus 1. Where if, in the case where n is 1, then the union from B1 up to B0 you should interpret as an empty union, so you're not deleting anything. Now, you can always do this, but where there might be trouble is, when you do this, do you get something that's in A mu? In this case, what we're doing is unioning a bunch of things and then doing some complement, right? That is in A mu for all n, because A mu we now know is an algebra of sets. So that is thanks to the fact that we already did steps 1 and 2. Steps 1 and 2. And the union, so if I take the union of the Bn's, I'm trying to show the union of the Bn's is in A mu, right? So the idea of doing things like this and deleting from each set what was unnecessary to be in it is that the union of the Bn's should equal the union of the Cn's. So each Cn is a subset of the corresponding Bn, so definitely we have this inclusion, right? And then if you're wondering about this inclusion, well, suppose you have X in this union, then it's in Bn for some n, right? But what you'd want to do is take the smallest n, such that x is in Bn. Then if you make n minimal with respect to the fact that x is in Bn, then you'll see that x is in Cn, because x would be in Bn, but not in any of these other ones due to the minimality of n. So we get both inclusions. So when you do this kind of thing, you do keep the union being the same. And also the CNs are pairwise disjoint, right? If you take like Cn and Cm, and let's say m is greater than n, then if m is greater than n, then Cn, well, it's a subset of Bn, which is literally one of the things that got deleted in our definition of Cm, right? Cm is Bm, delete B1 union Bm minus 1. So if m is greater than n, then Cn is contained in Bn, which is literally one of these things that we deleted here. So Cn and Cm would be disjoint. So the C's are definitely pairwise disjoint. So also the CNs are pairwise disjoint. Thus, by hypothesis, by our assumption that we have closure under accountable disjoint unions, that's in there, so that's in there. Okay, that's it for step 4. Not too hard. But the main thing I want you to pay attention to is that it required knowing that these CNs are in a mu, which requires knowing that a mu is an algebra of sets. So that required already having steps 1 and 2. This is why we had to build up so incrementally to do this.